Let's now discuss Ohm's law a little bit more in details. The most basic explanation to Ohm's law is the following. If I have a resistor R and I apply a potential difference delta V across this resistor, from now on we're going to call potential difference just applied voltage. Depending on the polarity of this voltage, I will have some current going through this resistor. Now, let's say my polarity is the following, where my positive is to the left and negative to the right. Well, in this case, my current will travel from left to right. And the relationship between these three would be V over R is equal to I. Or if I were given information for current and resistor, I could use that to calculate my voltage. So V is equal to IR. Now, what is the reason why current goes from positive to negative? If you remember, we said that resistors consume energy. So my current, when it enters the resistor, it must have higher potential than when it leaves my resistor, because it loses the potential to the resistor. So if you notice, positive terminal over here does have higher potential than negative terminal. So that explains it. So you can make a note for yourself that in circuits, current always travels from higher potential to lower potential. Using Ohm's law basic equation, we can now analyze resistors in series and parallel. So let's say I have two resistors in series, R1 and R2, and I'm going to connect them to a voltage source. So by now I know that there's going to be individual potential differences across these resistors, and I'm going to have a current I going from positive to negative terminal. So my I here, according to Ohm's law, should be the voltage provided to the circuit divided by its equivalent resistance. And from my resistor section, I know that series resistors simply add together. So V is equal to R1 plus R2. Now what I'm interested here is this V1 and V2 here. What are these individual voltages gonna be? Well, V1 is just I times R1. Remember, current is the same everywhere in this circuit. So I times R1, which I'm gonna replace the equation with R1 plus R2 times R1. And similarly, V2 is going to be I times R2, which is V over R1 plus R2 times R2. Now this equation, these two, are what's known as the voltage divider equation. And what it means is that basically, let's say V1 is R1 over R1 plus R2 percent of my overall voltage. So this fraction defines how big my individual voltages are going to be. So for example, if my R1 was smaller than my R2, then my R1 over R1 plus R2 would be smaller than R2 over R1 plus R2. And in conclusion, my V1 would be smaller than V2. So this is the main point for series circuits. Bigger resistors occupy or consume most of the potential. Repeating the same process for two resistors in parallel this time, I'll connect them to a voltage source V, and since the positive terminal of this voltage is in the same node as the top terminal of these two resistors, and the bottom terminal of the voltage source is in the same node as the bottom terminal of these resistors, I know that the voltage across these two resistors must be the same as my voltage source. So now that I have this information, I can say there's going to be current going from positive to negative terminal, which I'll call I2 and I1. And using Ohm's law, I know I1 is equal to V over R1 and I2 is equal to V over R2. And looking at this node over here, since there's no charge being destroyed or generated, then the current entering this node, which I'm calling I, must be the addition of these individual currents. So I'm going to replace this with the equation I found, which is V over R1 plus V over R2. I'm going to factor out V. And then I'm going to create a common denominator. And this is what's known as the current divider equation. So what's different here though is that this is the portion which corresponds to current R1. So if my R1 was less than R2, R2 over R1 R2 would be bigger than R1 over R1 R2. So now my current 1 is bigger than my current 2. And this is what's known as path of least resistance. So current always takes the path of least resistance. And if you have multiple resistors in parallel, the current in the smallest resistor is always going to be the largest. To summarize today's lesson, if I have n resistors in series, and I apply a potential difference of V across all of them, and let's say my resistors are arranged such that R1 is the smallest and Rn is the largest. And in this case, my individual voltage drops across these resistors is going to be such that V1 is the smallest and Vn is the largest. Where if I add all of these voltages together, I will get the voltage that my source provided. And so my current for all these resistors is going to be the same because they're sharing the same line. Comparing this to parallel circuits, if I have in parallel circuits now parallel resistors starting from R1 I'm connecting them to a voltage source, and let's say again my resistors are arranged such that R1 is the smallest and Rn is the largest, and this time the individual currents created in these circuits are going to be such that my I1 is going to be the largest. And again, since they're sharing the same node, then my voltage is going to be the same across all of them. And my overall current I here provided to the circuit is equal to the addition of all these individual currents. So two things about here is voltage drop across series resistors, which favors highest resistance, and in parallel circuits, path of least resistance, which gets the most amount of current.